Okay, good afternoon. Today we'll go for the topic called wiring capacitance. Topic is wiring capacitance. For that, just we'll go for a brief introduction part. First is intrinsic mass circuit. Just see the here the structure is mass structure, that is either it can be mass or P mass or C mass structure, that is a symbolic representation. Let's see here the three terminals of MOSFET. One is called source, gate and drain. Okay, when here the things called a capacitance. Capacitance is between the two layers. It forms under the two layers, the capacitance parallel plate. And it forms under the two parallel plates. There is a gate is on one plate and the source another plate. Between these two, here we have a capacitance called CGS. CGS is capacitance across gate to source. The capacitance across gate to source. Similarly, in between these two, that is between the gate and drain, that is CGD, and we know that there are total 4 terminals are there. 4 terminals are with respect to body. B is a body. Okay, here we have the source to body. CB is the source to body, and CDB is C capacitance, D is drain to the body. That is a diffusion, drain diffusion. The capacitance of drain diffusion, the capacitance of the source diffusion, the capacitance of the source diffusion, and capacitance across the gate to source, capacitance across the gate to drain. These are the capacitance across the different layers. Okay, the structure capacitance, channel capacitance, diffusion capacitance. They are called the structure capacitance, channel capacitance, and diffusion capacitance from the depletion region of the reverse bias PN junction. Okay, this is about the capacitance. First, we'll go for the what is meant by wire. What is the importance of wire? Then we'll go for the wire capacitance. First, we'll see the what is meant by wire. Okay, here chips are mostly made up of wires called interconnect. Chips are mostly made up of wires called interconnect. Okay, in stick diagram, wires have set size. In a stick diagram, I think you know that say for example, I have drawn a CMOS logic diagram, CMOS stick diagram. Say across the, I will use single color only for under two metal layers. First is the polysilicon, followed by the P diffusion, followed by the N diffusion. Then consider the polysilicon layer. Then we have one more polysilicon with this entire thing is called a transistor. P transistor, below is the N transistor. Okay, here we have to define a contact cut through the input. Here this is a simple stick diagram. Here the metal layers are wires between the connecting between the one layer to another layer. Wires are required. Interconnecting between the one layer to another layer, a wire is required. Okay, that size of the wire have been set, predefined. Okay, many layers are wire exist. That is a polysilicon. We need to have a polysilicon to diffusion to metal 1 to metal 2. They are the different layers. Wires being exist. Okay, next. Wires are the important as a transistor. Wires are the as important as a transistor. The important we have to connect externally. we have to interface and connect to the external world. Wires are required. As they determined, first parameter is speed, second parameter is power consumption, power, third is noise. Okay, and there are the parameter. Why the wire is important in a transistor? Because it influences the speed, it influences the power consumption, it produces a noise. Okay, these are the three parameters. One of the alternative way is layer run orthogonally. When you run a orthogonally, what is meant by orthogonal? Here the diffusion, you say a N diffusion or the P diffusion is orthogonally with the polysilicon. It is the, here these two are, we can call as orthogonal, perpendicular to each other. Okay, if you are use the two layers, say layer 1, second is the layer 2, these are called the parallelly. Layer 1 and layer 2 are the parallelly. If this type of the structure, then the capacitance will be more, the parallel plate. Here this produces a parallelly. When they parallel plate, then automatically capacitance comes into picture. Two layers, two conducting layers. When two conducting layers comes, capacitance comes into the picture. Here the only area, crossing area is small as compared to the parallel plates. Here when we use a orthogonally, perpendicular to layers are perpendicular. Here also see a metal layer is perpendicular to the diffusion layer. In this case also the capacitance is less. Okay, when we use a perpendicular layer, the capacitance value is less. When the capacitance value is less, delay is less. Okay, the connection, wiring connection should be made orthogonal to each other. Layer forming is orthogonal to each other. Okay, this is about the basic things why a wire is important in a transistor. Okay, three parameters they are influencing. One is called the speed, second is called power, third is called the noise. Okay, the based on the length and width of the wire, these things have been defined. Okay, next is the wiring capacitance. What is meant by wiring capacitance? What are the three sources of wiring capacitance? There are the other sources of wiring capacitance. Generally, area of capacitance plus the other parameter that influence the total capacitance. Okay, first in the last classes we have calculated the area of capacitance of the different layers, between the two different layers, say metal to the polysilicon, metal and diffusion. Like that we have calculated the different areas for the capacitance. Okay, in the previous example, area capacitance associated with the layers to substrate and from gate to channel. We have calculated that area. However, there are other significant sources of capacitance. Which contributes the overall wiring capacitance. Okay, it increases capacitance value. Okay, there are three such sources of wiring capacitance. Among that, first one is the fingering field. Okay, this is the one of the other source of the capacitance of wiring. Okay, for a fine line metallization, the value of fingering field capacitance CFF can be of the order of area capacitance. It is same as the area capacitance. It also fingering field capacitance. Also, it is a one major component in the area of the capacitance. It is similar to that. This is a direct formula. CFF equal to epsilon silicon dioxide, epsilon inverse, that is 4 epsilon naught. These are the two constant parameter. L, okay, L within bracket pi divided by ln of 1 plus 2d divided by T within bracket 1 plus root of 1 plus T divided by T bracket close minus T divided by 4D. Okay, here just we have to remember this formula. There is not right way for this one. In this, what are the things? Wire, that wire L, here L is there. This L, there are things called the L. This L is the wire length. L is the wire length. Here that things called T, and here also T. This T is the thickness of wire. It is direct, that CFF is directly proportional to the length of the wire, inversely proportional to the T, as well as inversely proportional to the D fact. D is the wire to substrate separation, spacing between the wire to substrate spacing. Okay, then total wire capacitance is C area plus CFF. This is an CFF is an one more parameter. It influences the wire, that is wire capacitance. That is, previously we have calculated only area of the capacitance. This is one more parameter, factors. It is called the CFF. It influences the these are the three parameters. That is called the L, length of the wire, thickness of the wire. D is the wire to substrate separation. Okay, దీని తర్వాత మరోసారి చెప్తాను దీని గురించి. Okay, second is I have told that there are the three parameters that the accurate production of performance is need to be considered. There are the three parameters. One is called the fingering field. Second is called the interlayer capacitance. That is one layer to another layer. There is one more layer, that is interlayer capacitance. That is capacitance between the layer due to the parallel plate effect. Capacitance between the layers, different layers, due to the parallel plate capacitance, parallel plate effect. Knowing this capacitance, the accuracy of the circuit model and delay calculation will be improved. If you know these parameters, that is, one is called the fingering field capacitance and interlayer capacitance. Third is the peripheral capacitance. If you know these things, the accurate value can be found. That is, a capacitance value can be found. Okay. This also next a peripheral capacitance. The peripheral capacitance is in the N diffusion region or the P diffusion region form a junction with N well and P well respectively. Okay. Next, in the diffusion region, that is from diode structure, CP is the peripheral capacitance increases with reduction in the source or drain area. Okay, this peripheral capacitance increases when you reduce the areas, that is diffusion. It is for example, say for a in the take the a P mass device, N mass, in that P is in a substrate, diffusion is the N type. The area, this area, N diffusion areas, this N diffusion area, if you reduce this N diffusion area, automatically the peripheral capacitance is going to increases. That is in terms of the picofarads per unit length. It is the capacitance of peripheral. The only thing is CP increases with reduction in the source to drain area. Okay, there is a predefined areas we have to maintain. A total diffusion area is diffusion capacitance area is C area, C, that is C capacitance area plus CP area. Okay. These are the some predefined things called the area and peripheral areas. Okay, for a diffusion capacitance, for an diffusion area, that is C area equal to, for 5 micrometers This is 1 into 10 to the power of minus 4 picofarad per micrometer square. For a peripheral, that is a CP, is 8 into 10 to the power of minus 4. It is larger. For a 2 micrometer and 1.2 micrometer, it is negligible. We can omit that. Assuming implant region are negligible depth, it can be eliminated. It can be leaved for a 2 micrometer and 1.2 micrometer. For the 5 micrometer technology, the peripheral capacitance is larger than the area of the capacitance. That is 1 into 10 to the power of minus 4. Here it is 8.0 into 10 to the power of minus 4. Okay. Next, here we have the different layers within a different technologies. They are the values, predefined values. Maximum length of communication wire. Okay. Metal. It is based on the chip wide. The metal can be based on the chip wide only for the 2 micrometer and 1.2 micrometer itself. For the metal, the sheet resistance and sheet capacitance, that is square Cg and square Rs value is low. For a metal, it may be the 1 centimeter or 1 micrometer width. The sheet resistance and capacitance will be less. For silicide, it is 2000 lambda. Afterwards we can define that lambda based on our requirement. It is not applicable for the 2 and 1.2. Here just say that things called the only thing is with respect to the polysilicon, it is 200 lambda, 400 lambda, 250 lambda, and diffusion 220, 100, 60. Okay, the value is going to varies. In the silicide, resistance value is resistance value is low and capacitance value is moderate. Okay, polysilicon, when you go for a polysilicon, the resistance value is high. For a polysilicon, the resistance value is high and capacitance value is low. And last one is the important diffusion. For a diffusion, resistance is moderate, capacitance is high. Only thing is the resistance and capacitance value are high for the polysilicon and diffusion. Resistance values and capacitance values are high for the polysilicon and diffusion. These two are influencing the delay factor. The delay factors are defined by the polysilicon and the N diffusion areas. That is maximum length of communication wires. If you should not go behind this, that is 200 lambda and 400 micrometers and 250 micrometers size. These are the size. Wire length sizes. It is a maximum wire length size. Okay, for that these are the defined things. Next topic is the fan in and the fan out. What is meant by fan in? Fan in is the number of inputs to the gate is called fan in. Number of inputs, how many inputs are being driven, have been connected, that is input side. Okay, fan out is at the output side. Fan in is the input side, fan out at the output side. Output is the maximum number of similar gates that a gate can be drive while remaining with the guaranteed specifications is called fan out. Number of outputs, number of inputs, number of outputs. That's simply fan in is the number of inputs to the gate is called fan in, number of outputs to the gate. Okay, that is fan in and fan out. There are the effects of the fan in and fan out. Okay, effects of fan in and fan out on propagation delay. Overall thing is called purely all this concept, entire concept purely on the only one topic called the propagation delay. Okay, if you increase the number of inputs, if you increase the number of outputs, what is a thing we need to consider for the propagation delay? In addition, additional inputs to the CMOS logic gate requires an additional NMOS and PMOS, that is 2 additional transistors are required. If you increase an additional input to the CMOS logic gate requires an additional NMOS and PMOS, that is 2 additional transistors are required. While in case of the other mask logic gates, it requires only one additional transistor. In CMOS logic gate, due to these additional transistors, not only the chip area but also the total effective capacitance per gate also increases. Hence, the propagation delay also increases. Okay, for an CMOS propagation delay is more. Finally, some of the increase in propagation delay time can also be compressed by the size scaling method. By increasing the size of the device, its current driving capacity can be prescribed. Okay, due to increasing the both inputs and device size, capacitance increases. Hence propagation delay will still increases with fan-in. If you increase the device size, automatically the capacitance increases. When capacitance increases, already you know that tau equal to RC. Okay, if you increase the C, automatically it increases the tau. Hence the propagation delay will also still increases with fan-in. Next, an increase in the number of outputs of the logic gate directly add to its load capacitance. Hence the propagation delay increases with fan out. If you increase the number of outputs, automatically propagation delay also increases. If you increase the size, that is die size, capacitance increases. As capacitance increases, propagation delay also still increases as with fan-in. Okay, it is about the fan-in and fan-out. Okay, next is the choice of the layers. Already you know that 4 layers. 4 layers are the polysilicon layer, a diffusion and p-diffusion, and one more is the metal layer. Okay, the following are the constraints which must be considered for the proper choice of a layer. First one, since a polysilicon layer has a relative high specific resistance RS. RS is high, as I told in the figure in the previous chart. I told that resistance, sheet resistance value is high for polysilicon, and for diffusion capacitance is high. In the previous slide I have told that thing called since the polysilicon layer has a relative high sheet resistance, specific resistance, it should not be used for routing VDD and VSS. For routing VDD and VSS, we should use the metal layer, because the metal layers are less resistance, sheet resistance. For VDD and ground, VSS must be distributed only on metal layer due to the concentration of or constant sheet resistance. Okay, here the polysilicon layers should not use for the routing, because the sheet resistance value is high for the polysilicon. Okay, we should not route the VDD and VSS by using the polysilicon. It should be used by the metal layer only. VDD and ground, that is, must be distributed only on metal layer due to the that is low sheet resistance value. Okay, next is the capacitive effect will also improve certain restriction in the choice of the layer. Okay, we can reduce, we can improve. How to improve the how to reduce the capacitive effects? First is a resistive effect, second is a capacitive effect. Wherever fast signal lines are required and is a realization to signal on wiring which has relatively high value of sheet resistance. The diffusion area have higher value of capacitance due to substrate and are hardened to drive. Okay, these are the two things. It can be affects capacitive. Next, fourth point, over a small equipotential region, the signals on a wire can be treated as being identical at all points. Within each region of propagation, delay of the signal will be comparatively smaller than the gate delay and signal delay caused in the system connected by the wire. Just here you need to note that two basic things it can be influencing, that is a choice of layer. VDD and VSS line must be distributed on a metal line due to low RS value. It is the first point. Second is long length of polysilicon must be avoided because they have larger RS. We should not use a metal for the flowing a VSS and VDD lines on a polysilicon. Long length of polysilicon must be avoided because they have a larger RS. These are the 2 points related to the RS. The resistance effect of the transistors are much larger, hence wiring effect due to the voltage divide effect between the wires and transistor resistors. Diffusion areas must be carefully handled because they have larger capacitance to substrate. The diffusion area is the basic thing is that if they more diffusion, then automatically capacitance is more. If you reduce the diffusion area, automatically one more is there, that is the peripheral capacitance increases. They are the things, they are interrelated. If you want, the thing is called, we should decrease the diffusion area, that is diffusion area must be carefully handled because they have larger capacitance to substrate. Okay, these are the things. Choice of the layers, what layer we should use and what should be the values for sheet resistance and capacitance. The thing is only 2 things. One is called polysilicon has a higher resistance, sheet resistance value, and diffusion has a higher value. The only two things we should take care for the diffusion area. We should not use, we should avoid the longer length of polysilicon. That by using the VDD and VSS lines must be distributed on a metal line due to low resistance. These are the choice of the layer. Okay, what are the things for the metal? They are the low, for silicide low, medium, polysilicon high, moderate. That values diffusion, capacitance is high and resistance is low. These are the things. This is an important chart. Okay, this is about the your half model. That metal is good current capability without large voltage drop, use of power distribution and global signal. For the silicide, only for 5 micrometer we are going to use silicide. Polysilicon for the RC product is moderate, high IR drop. For the diffusion, moderate IR drop but the high C, hence hard to drive. Okay, this is an important chart for a choice of the layers. Okay, next class I will go for the gate, logic gate using CMOS. Already we have been discussed NAND gate, NOT gate, CMOS things. I will review that. Then we'll go for the complex gates, switching logic, alternative gate circuit, pseudo NMOS logic and dynamic CMOS logic, clocked CMOS logic, that is C square MOS, CC is the clocked CMOS, and cascade voltage switching logic. Next class we will go for this second half of the model. Till now we finished the first half of the model. If you have any doubts, you can ask. The topic is little bit complicated. That is, one is called the wiring capacitance. Second is called fan in, fan out. Anyhow, it is quite a simple thing. Choice of the layer. Almost this completes our half of the model. Okay, next class onwards I will start with the gate level design. This is one of the important topics. Generally in the particular textbook you will find from the subsystem design and layout. In that you will find that gate level logic. The Bucknell, I will refer only the textbook called Bucknell VLSI system design. VLSI circuit and system, essential for VLSI and circuit system by Bucknell, Pucknell, Bucknell textbook. Okay. If you have any doubts, you can ask, otherwise we'll wind up today's class.